In this lesson, we'll look at how to convert between the vector form and Cartesian form of a line in 2 dimensions. So we're going to start with points A and B. A has coordinates 1, 6 and B has coordinates 5, 4. We're going to find the equation of the line passing through A and B in both their vector and their Cartesian forms. So first, the vector form. For this we need the position vector of a point on the line, and we also need the direction of the line. So for the position vector, we could use point A, 1, 6, and to find the direction, we need to use the position of A and B, and the fact that the vector A to B is the position of B minus the position of A. So we're going to get 4 minus 2 as the direction vector of the line. We can then put that together into a vector equation to give us r equals 1, 6 plus lambda 4 minus 2. Now to find the Cartesian equation. So for this we need to know the gradient of the line. So that can be found by finding the difference in y divided by the difference in x. That gives us -1/2. We can then use any of the equations that we use to find the Cartesian equation of a line, either y equals mx plus c or y minus y1 equals mx minus x1. Putting that together and rearranging gives us the Cartesian equation 2y plus x minus 13 equals 0. Now, because these represent the same line, they must actually be the same equation. We're going to look at, would it be possible to convert between the two? So if we start with the two equations, the vector equation and the Cartesian equation here. So the position vector r represents a point on the grid. Remember that r is just the vector x, y. So we could write this equation as xy equals 1, 6 plus lambda times 4 minus 2. If we separate this into components, we get the x component is x equals 1 plus 4 lambda, and the y component is y equals 6 minus 2 lambda. That has just come from reading across the top line and then reading across the bottom line. If we want to make the Cartesian equation, we need to eliminate lambda. So we're going to rearrange both equations so that lambda is the subject, and then we can put them equal to each other, eliminating lambda. So the first equation becomes lambda equals x minus 1 over 4. The second equation becomes lambda equals 6 minus y over 2. So putting the right hand sides equal to each other, we get x minus 1 over 4 equals 6 minus y over 2. We can then rearrange this and we get the Cartesian equation that we found earlier, 2y plus x minus 13 equals 0. Now I'll pause the slide, and for each of the 4 vector equations, use the method in the previous example to write the Cartesian equation in the form y minus y1 equals mx minus x1. So for the first one, we're going to get from the x component that x equals 3 plus 2 lambda. From the y component, we get that y is minus 1 plus lambda. Rearranging the two, we get lambda equals x minus 3 over 2 and lambda equals y plus 1. Putting these together, we get x minus 3 over 2 equals y plus 1 over 1. Rearranging this gives us the Cartesian form in the form y minus y1 equals mx minus x1, which we are familiar with. For the second, the x component is x equals 5 minus 2 lambda. The y component is 1 plus 8 lambda. So rearranging these two, we get lambda equals 5 minus x all over 2. For the second one, we get lambda equals y minus 1 over 8 Putting these together gives us the Cartesian equation there. For number 3, the x component is minus 4 plus 5 lambda. The y component is 0 plus 3 lambda. So lambda is x plus 4 over 5. Lambda is y over 3. Putting these equal to each other gives us the equation shown. And for the 4th one, the x component is minus 1 plus 3 lambda, but we can see the y component is just minus 2. There is no lambda component here. So for this one, we have that lambda can be written as x plus 1 over 3, and also that y plus 2 is equal to 0. In this case, the most appropriate way of writing the equation is that y is always negative 2. X can be any value depending on what value lambda takes, but because y is always minus 2, this represents the horizontal line y equals minus 2. So to summarise, in 2 dimensions, if the vector equation of a line is r equals a plus lambda b, or in component form r equals a1 a2 plus lambda b1 b2, then to rearrange this into Cartesian form, we get y minus a2 equals b2 over b1 x minus a1. You may recognise this as being an alternative form of the formula we use to find straight lines, y minus y1 equals m x minus x1, as the value of m here is the gradient. Now complete the following questions in exercise 9b on page 204. This is the 2-dimensional questions only, so question 1a, I and II, question 2 and question 5.